Hey kiddos, and welcome to section 15.2. This is all about Le Chatelier and what is going on with equilibrium. What happens when we add more products? What happens when we add more reactants? What is going on? This is actually, I really enjoy Le Chatelier. I think it's quite fun, but give it a minute, listen to the podcast, listen to some videos, or watch the videos that I asked you to. Let it sit with you for a while before you do some practice. Okay, so according to Le Chatelier's principle, when a chemical system in equilibrium is disturbed by a change in property of the system, so there's a change in the system. The change in the system could be various things. It could be a change of concentration of the reactants of the products. It could be a change in temperature, and it could be a change in pressure. So we're going to talk about all of those changes and what happens when we apply those changes. So the system always appears to react to oppose the change until a new equilibrium is reached. Okay, that's the concept that we're looking at. Something's going to change abruptly and then it's going to go to equilibrium. And we're going to take a look at, oh, actually, once you figure out Le Chatelier, you'll be able to predict what kinds of changes are happening. So I'm going to talk about the theory first, and then I'm going to show you how to, the same theory, but how it looks like in a graph. Then we're going to just stop there. And then later I'm just going to make a little kind of behind the scenes, looking at the chemistry and what it looks like if we had a lab. Okay, so the application of Le Chatelier's principle involves three parts. We're looking at the initial equilibrium state, right? So before anything happens, a shifting non-equilibrium state. So here we're going to change it up. We're going to add something, take something away, increase the temperature, increase pressure or decrease pressure. And then once we have this, once we've changed it, once we've added something to the to the to the whatever we're looking at, we're going to have a new equilibrium state. So Le Chatelier's principle provides a method of predicting the response of a chemical system to an imposed change, such as we're going to talk specifically about change in concentration, we're going to talk specifically about change in temperature, and change in pressure. Now with change in pressure, the only thing you have to keep in mind is it only happens with gases. Okay, so here we go. This is what happens. This is what you need to know. The addition of more reactant, so if you're adding more of a reactant, this will cause the system to shift to the right. Okay, what does that mean? A plus B yields C, right? If I'm adding more of a reactant, let's say I add A, it's going to shift to the right. This equilibrium is going to shift to the right. Why? This means that the system will produce more products to compensate. If I'm adding extra A in there, all of a sudden, it's kind of like a teeter-totter, right? If I'm adding more A, this is my teeter-totter. If I'm adding more A, you'll see that there's an imbalance, right? In order to balance this, I have to add more of the products. And that's what we mean by a shift, right? There's a shift to the right. In this case, the shift is going to tell us that we need to add more products to get to equilibrium. And this shift is you can explain it using or you can articulate it using sentences, or you can also show it using graphs, which we'll do later. The removal, because we're talking still about the reactant, the removal of a reactant will cause the system to shift to the left, okay? So this means the system will reverse the reaction to produce more reactants to compensate. What does that look like? I have A plus B, right, yields C. If I take away a reactant, if I'm taking away A, what's going to happen is it's going to look like this, right? So what's going to happen in order for me to flatten or to get to equilibrium, I have to add more reactants, right, to get to reach equilibrium. Does that make sense, kiddos? Okay. So let's talk a little bit about what's going to happen if we play around with the products. You can sort of see it starts to be quite intuitive. The removal of some product will cause the system to shift to the right. This means that the system will produce more products to compensate. So if I'm taking away a product, the equilibrium will shift to the right. So I have again A plus B yields C, right? If I take this away, I'm going to have this kind of thing. That's my teeter-totter. I have to add more products to go from that to reach equilibrium. The addition of a product will cause a system to shift to the left. That makes sense too. This means that system will reverse the reaction to produce more reactants to compensate. Okay, if the item added is not part of the reaction at all, then its job is to remove something from the reaction. Remember to use your solubility table here. Now, in this case here, what you're doing is when you're adding something different, you're basically causing a precipitate to form. But I'll go into that a little bit more detail later, because right now you just have to worry about how things are shifting. This is just a little foreshadowing of what may be to come. Changes in temperature. So for changes in temperature of a system, we need to look at whether the reaction is exothermic or endothermic. We treat the heat energy, right, in a chemical equilibrium as though it were a reactant in an endothermic reaction or a product in an exothermic reaction. What that means, if I have A plus B, right, if it's an endothermic reaction, remember that the energy is on the reactant side. This is for endo. Now, if we're looking at exothermic, right, we have A plus B. We have the energy as a product, right? And when we're talking about these equilibrium changes and shifts to the products of reactants, we think of this energy as an entity, okay? So if I increase the temperature, what I'm actually doing, right? If I increase the temperature, right? If I'm increasing the temperature, what I'm actually doing in an endothermic reaction is I'm increasing the reactants. In an exothermic reaction, what I'm doing is I'm actually increasing the products. Does that make sense? And then when I'm increasing the products, for example, here, if I'm increasing the products, it's going to shift to the left because I need to compensate for that. And so just think about it. Think about when you're adding or taking away temperature or heat. Think of it, first of all, is it exothermic or endothermic? And then think about where that energy lives in terms of the reactants of the products. And then you can pretty much predict it. It becomes much easier to predict. So I'll articulate that for you. For an endothermic reaction, we have reactants plus energy yields products, right? In an equilibrium, we have those double arrows. Heating up the reaction will cause the system to shift to the right. This is because the heat energy can be thought of as a reactant, right? Your heat energy is like a reactant. Therefore, adding more reactant causes the system to shift to the right, which is really shifting to the products. Shifting, okay, can't spell there, that's okay. To products to compensate, right, for an excess of reactants. Cooling down the reaction will cause the system to shift to the left. This is because cooling removes energy. We are removing some of the reactants, so this system shifts left. If I'm cooling it off, I'm removing a reactant, right? If I'm moving a reactant, looks like this, I'm going to have to add more reactant to make it reach equilibrium. So for exothermic reactions, the energy is a product because it's shown in the product side, so it's actually like an entity. Heating up the reaction will cause the system to shift to the left. This is because the heat energy can be thought of as a product, therefore adding more product causes the system to shift to the left or to shift to the reactants. Cooling down the reaction will cause the system to shift to the right because I'm removing a product, right? Because heat is considered a product. So that's pretty good. So note, for changes in temperature or concentration, we see that equilibrium will shift to the opposite side of an addition shift to the same side of a removal, okay? Change, so that's like a general rule that pretty much always makes sense. Changing the temperature of the reaction will change the equilibrium constant, okay? So the only thing that will change your equilibrium constant is changing the temperature. So changing the temperature of the reaction will change the equilibrium constant. All other changes do not change the equilibrium constant value, only changing the temperature. So let's talk about changes in pressure. So changes in pressure have to do with gaseous entities only. This deals with the chemical equilibrium of gaseous systems. If you recall from earlier science classes, a gas experiencing a change in pressure will also experience a change in volume. So the question might say increase the volume. If I'm increasing the volume of something, I'm actually decreasing the pressure. If I'm decreasing the volume, because they're inversely proportional, right? If I'm decreasing the volume, I'm actually increasing the pressure. To predict how a change in pressure will affect the system's equilibrium, we must look at the total amount of moles of reactants and the total amount of moles of products. And we'll look at a specific example a little later on. This only works for gaseous systems, and a change in pressure does not affect any gaseous system with equal mole counts. If there's equal number of moles on the products and the reactants, you will not get a shift. Sometimes a catalyst, if you have a catalyst, kiddos, if you're adding a catalyst, remember a catalyst is something that you add that's not consumed. Because it's not consumed, it's never, ever, ever going to cause a shift in equilibrium. It's just going to help the reaction occur faster. Recall that? It only speeds it up. It does not change or cause any kind of shift because it's not consumed. A catalyst is never consumed. So let's take a look at the graphs, and this is where we're going to take a look at things a little bit more closely. A change in energy or temperature results in all items gradually changing. Because when I change something, right, let's say A plus B plus energy, for example, yield C. If I'm increasing the temperature, for example, I'm not just increasing the temperature of entity A or B, I'm increasing the temperature of the whole thing. So it's going to react in a certain particular way. Just like if I add an extra entity to increase the reaction or the reactant, I'm not just adding it to the reactant, I'm adding it to the whole system. So keep that in mind. Okay, a gradual change is depicted as a curve, either up or down. To determine whether the change was an increase or decrease in energy, one needs to know if the reaction is endo or exo in nature, as well as looking at the results after the change. So I'll show you what these graphs look like in a bit. A change in concentration involves a dramatic change. A dramatic change is depicted as a spike, either up or down, and I'll show you what that looks like a little later. So you have a spike rather than a gradual kind of curve. To determine the type of change, just look at which way the spike is going as well as which item it's dealing with. If it's going up, then it's an increase. If the spike is going down, it's a decrease. And you will be able to tell the difference between a spike and a curve. A change in pressure involves a dramatic change in all items. This is really important for pressure. If I'm increasing the pressure, I'm going to have a spike. Depending on what's going on, there's going to be a spike right away, and then it's going to teeter into a curve going up or a curve going down. To determine the type of changes, look at which way the spikes are going. So either you're going to have a spike up or you're going to have a spike down. So what do these look like? Before we start dealing with these, let's take a look at a flat line. Represents a constant concentration, which means equilibrium. A curve up. So this is your curve up, means a gradual increase in concentration. This actually is a curve down. This is what it looks like. Represents a gradual decrease in concentration. And a spike up or down represents a drastic change that is occurring. And I'll show you what those look like in just a bit. Okay, so let's take a look. Now I'm going to say the same thing. I'm going to repeat myself, guys, but I'm going to repeat myself in a way that hopefully will help you understand in terms of what it looks like in a graph, what these shifts look like in a graph. When I said shift to the right, shift to the left, shift to the products, shift to the reactants. That's great. I know that it's not difficult to understand, but how do we see that or understand that when we look at a graph? So the addition of a reactant to a system at equilibrium produces an equilibrium shift forward or towards the right. The forward reaction produces more product molecules to oppose the change introduced. So here's an example. We're going to take that liquid away because that's not part of it. Here are our entities, okay, kiddos? We have one of our reactants and our products, right? And here's that spike. See the spike there? That's a spike, and this is a gradual curve, okay? So in this case here, it says we are adding, let's see, an addition of the reactant. So this shows that there's been an addition uh, of the reactant. So there's your spike. This tells me, hey, I added this. I added a reactant. And then what's going to happen, this also shows, see how this is a curve up? This is after the spike, after this line here. This is showing the reaction, or the how the system is reacting to the addition of the reactant in this case. Notice that after this has been added, your products are going up because it's compensating, right? Because it's going to the shifting to the right. And then all of a sudden, because it shifts to the right, there's a down. There's like a little downward because it's compensating for that. So as more products are formed, less reactants are being seen after the initial spike. So the sudden upward spike in the hydrogen fluoride gas indicates that hydrogen fluoride is added. And the equilibrium shifts to the right is indicated by the gradual decrease in concentration of the reactant and the gradual increase in concentration of the products. Okay, the removal of a product will also shift the equilibrium forward, producing more product molecules to oppose the change introduced, which we've talked about. So we don't include the liquid there, the carbon tetrachloride, we don't include that. So here we go. Here's our spike, right, downward. You'll notice that there's a spike downward here. Spike downward, little, and then we have what's going on in order to compensate for that. Okay, so see how there's like a little kind of upward, slanty kind of slope? That's telling you that it's compensating for that removal, right? And then all of a sudden here, this is going down. So that makes a little bit of sense. Now, here's another thing that's very, very important. Notice that it's a 2 to 1 to 2, right? So you can see that in the fact that this, oh, it's so hard to see, but this is a really small amount, right? Right, because it's only a 1 here. And here for the 2, you'll notice that it's a larger space, I guess, than this one here. And this one again is quite large too, because there's also 2 here. So there's going to be a change in the width of these curves. So very important that you notice that as well. So the sudden downward spike in hydrochloric acid, or gas in this case, hydrogen chloride gas is removed. So it shows there's a spike going downwards. The equilibrium shift to the right is again indicated by the gradual decrease in concentration of the reactant and the gradual increase in the concentration of the products. Okay. Changing concentration has no effect again on the value of the equilibrium constant, only change in temperature. But just be aware too, like I said, be aware that these coefficients are going to dictate the width of these changes. See how little that is compared to these guys? Because this is where you have your coefficient of 1 and these are your coefficients of 2. So just be aware, little things, little nuances. Collision reaction theory and the concentration changes. Here's an example of real life, not going to be tested on, this is just FYI. When we increase the concentration of reactant, we assume the collisions between the reactants are much more frequent, significantly increasing the rate of forward reaction. As the concentration of the products increases, so does the rate of the reverse reaction, and the rate of the forward reaction decreases as reactant molecules are used up. Eventually, the rates become equal and a new dynamic equilibrium is changed. So we get that kind of thing with I guess, taking air from our surroundings and bringing them into our blood vessels and our capillaries and our lungs, etc. So let's take a look at temperature changes. In endothermic reaction, energy is an entity that's found on the reactant side. And for exothermic reaction, energy is found on the product side. Heating or cooling is like adding or removing. Remember heat energy from the system, which you already know. Here's an example of an endothermic reaction. So heating shifts the equilibrium to the right. So heating it, you're going to increase the reactant. which is going to cause a shift to the right so that that compensates for that, the more products are formed. And cooling shifts the equilibrium to the left. So let's take a look. Let's kind of revisit thermo a little bit. The negative enthalpy change indicates the reaction is exothermic. So heating shifts the equilibrium to the left, and cooling shifts the equilibrium to the right. So this is what it looks like, kiddos, in terms of a graph. The gradual increase in concentration of the product with a gradual decrease in the reactants indicates a shift to the right. Now, notice as well that it's a 2 to 1 to 2 ratio. So notice that the only oxygen has a smaller little bit here. This is way taller, and this is way taller. Okay, it's just something to notice. The system has been cooled. The shift to the products increases in the value at the value of the equilibrium constant. Very important here. The shift to the products, if I'm shifting to the products, it's going to increase your equilibrium constant. So here's another example. Cooling the system decreases the rates of both the forward and the reverse reaction because the particles move slower and collide less. But the reverse rate decreases more than the forward rate, resulting the production of more product and the release of more heat energy. So let's take a look at more specifically what happens when you play around with pressure, okay? Or volume, because volume will affect pressure. And remember, it's an inverse relationship. Recall that pressure and volume of gases are inversely proportional. An increase in volume, which is actually exactly like saying a decrease in pressure, will cause a shift toward the side with a larger number of moles. This is what's important now. You have to actually count out how many total moles you have in the reactants of the gases as opposed to how many total number of moles of your products, okay? And a decrease in volume or an increase in pressure will cause a shift toward the side with a smaller number of moles of total number of moles of gaseous entities. So here's an example. Where is it? Here we go. In this example here, we have 2 moles of this reactant gas, plus you have 1 mole of oxygen, right? So total reactants, you have 3 moles of gases. As opposed to your products, you have 2 moles of gaseous products. Okay, so if the pressure is increased, there will be a shift towards the products because the products have a lesser amount of moles. If the pressure is decreased, there will be a shift towards the reactants because there are higher number of moles of the reactants. So this is what you do. You have to actually count the total number of moles. A system with equal amount of gases on each side is not affected by change in volume. The same for systems with liquids or solid entities. They're not affected by pressure changes or volume changes. Adding or removing gases that are not involved in the system may change the pressure, but does not affect equilibrium. Okay, here we go. Here's an example. A volume or pressure change will produce a spike in concentrations of all gaseous entities followed by a gradual equilibrium shift. Notice that here's our spike. We have a spike here, we have a spike here, and we have a spike here. And then we notice that there's a gradual change. This is going down, and here we have something increasing. The product is increasing, right? An increase in products shows that there was a shift towards the products. So the sudden increase in concentration of all gases indicates that the volume has been decreased. In other words, pressure has been increased. Changing the volume or the pressure has no effect on the value of the equilibrium constant. Remember, only temperature. So let's summarize. For concentration, if we have an increase in concentration, right, of an entity, shifts to consume some of the added reactant or product. If there's a decrease, shifts to replace some of the removed reactant or product. For temperature, if you have an increase, shifts to absorb some of the added energy. A decrease shifts to replace some of the removed energy. And for volume, this is only with gases, an increase in volume or a decrease in pressure shifts toward the side with the larger total chemical amount of gaseous entities. Chemical amount is number of moles. And we look at our coefficients for that. And a decrease in volume or an increase in pressure shifts towards the side with the smaller total chemical amount. Remember, that's number of moles. Temperature, again, is the only change that will affect the value of the equilibrium constant. And that's it, kiddos. So let that really sit with you for a while before you attempt some practice. Have a nice day.